Now, we are already very clear about the characteristics of a population defined by the measure of a central tendency, namely the population mean mu, and also by the measure of dispersion, the population variance sigma squared. Right. So, in order for us to actually find good unbiased estimators of these two parameters, we select appropriate samples. Alright, and then from there we use the data from the samples to actually to act as good estimators of these population parameters. Now there is also a possibility that this sample here is not the only possible sample that you can get the data from. What you can do is you could actually have many different samples of similar size. Right, so maybe for this one you have a specific mean, this one is another mean, this one is, and so forth. Right, and it goes the same with the sample variance as well. So each one of these sample will have its own specific sample mean. This means that the sample means of this population will actually have a certain distribution. Alright, by now we might want to think that if we are able to have a distribution for the sample means, then what kind of distribution would it be? Alright, so before we go into the distribution of the means, okay, let's see whether how does it look like to actually find the sample means of a certain random variable with an example 9. Okay, so in example 10 we are given a population consisting of numbers from 0 to 99. So this population actually have a size of maybe 100. So samples of 5 numbers are selected and the following are found. Okay, in the first sample there's 51, 77, 27, 46 and 40. Second sample, and so on and so forth. Altogether there are 6 such samples. Now we are then asked to calculate the means of these samples. Now the mean of each sample can be found by using this formula that you have already known. In this case, each one of the sample actually have about only 5 items, right? So using this formula we can actually find the sample means of each one of them, right? So from this example, it is evident that the sample mean can take different values, alright, and therefore x bar is the representative variable representing all these sample means. Okay, so this means to say that sample means actually have a distribution. By now we might want to think that if we are able to have a distribution for the sample means, what kind would it be? So before we go into that, okay, let's say if x1, x2 and x up to xn is a random sample of size n taken from an infinite population, and this population has mean mu and variance sigma squared. Then the sample mean x bar is a random variable with expected value of x bar as mu and the variance of x bar as sigma squared over n. Alright, now this can be easily proven by the following. For the proof of the expectation of x bar is similar to how we wanted to find the unbiased estimate of the population mean. Right, the proof is similar as what you see here. For variance of x bar, alright, we can implement the same kind of idea, but in this case, alright, the variance of x bar, which consists of the variance of x1 plus x2 all the way until xn divided by n. Now we know the property of independent random variables. If x1, x2 all the way up to xn are independent, we can actually add them up as what you see here. Alright, now the only other property that you need to take note of is for variance is, since in this case, right, n is within the bracket, when you take it out, okay, you actually have 1 over n squared. Right, now since variance of x1, variance of x2 are all derived from the random variable x, Alright, so each one of them will have a value of sigma squared, which is similar to the variance of x itself. Okay, ultimately then you will actually arrive to this solution as sigma squared over n.